Paper is 3D triangulation for industrial applications by Cavalcanti, Atencio, Esperança e Nascimento, Paulo Ronald the talk.
Hello. The title of this work is 3D triangulations for industrial applications. Is a work developed at UFRJ, and the goal is to be able to create triangulations for 3D non-manifold models given as a set of polygonal surfaces. We have chosen to use the CEGRAPI library because it offers a lot of very nice data structures. And we know that CEGRAPI library has procedures to produce 2D or 3D triangulations. But in our cases that we want to use the input by means of polygonal surfaces, the creation of the constrained triangulation is still limited. The nice thing about using CEGRAPI is the robustness, because it offers a lot of kernels that we can use to have a robust implementation that always accomplishes the generation and creation of triangulation. We have used an object-oriented approach. We implemented everything in C++. We use CEGRAPI in STL. And as an interface, we use the Qt and OpenGL. And the system runs on the main platforms available, such as Linux, Windows, and Mac OS. Well, we know that we have three main families of algorithms for performing triangulations. Basically, we have octree-based methods, Delaunay-based methods, and advancing from based methods. Well, each method has advantages and disadvantages. And for instance, advancing from generates very nice tetrahedra near the boundary, but they have problem when merging the different froms coming from different directions. Delaunay, on the other hand, tend to generate good tetrahedra inside the model, but near the boundaries, the tetrahedra may have, can be badly shaped. And in our implementation, we decided to use a Delaunay-based approach. As I have said before, CEGRAPI has functions for input models, either bounded by 2D manifolds, mesh, or by means of an implicit function. In our case, we are interested in multi-region models defined by several non-manifold surface meshes. And they cannot be input directly in CEGRAPI, but only by means of an implicit function or a scalar field. The main reason for this is that surface boundaries are represented internally in CEGRAPI by means of a half-edged data structure. In this case, this data structure is not adequate to describe non-manifold domains, just the kind of domain we are mainly interested. Here we have a very simple model showing the type of domain that we are trying to triangulate. In this case, we have a box, two surfaces, we call in geological models, we call this a horizon. We have a fault here, we have dangling faces, and three regions. This is a more complicated model. We have a dome of salt here, And we have a region here, another one here, maybe 4 regions in this model. And this is what we could do using Segal. We would have to transform our input in an implicit domain to obtain the final triangulation here. As we can see, the boundary is only approximated using this methodology. This may be acceptable in some applications, but we have some cases where this is not what we would like to have. We would like to honor the boundaries all the time. We have mainly interested in geoscience models. And in this case, our models are mainly 3D non-manifold. And we have a lot of dangling faces. And it's not natural to describe this using an implicit function. It's possible, but it's not the way we would like to work. To deal with such kind of complex models, we proposed a solution by breaking the model into a set of simple surface patches be called fragments. These fragments can be represented in Segal using the half-edge data structure. Then we have another data structure to describe the topology of our model. In this case, we just need to use some lists available in the STL library. This is a typical multi-region model. We can see the Dome of Salt here, a big region here. And this is the type of model we would like to triangulate. So, very fastly, our data structure defines a vertex, the coordinates of each vertex in the model. We have faces described as a set of loops. A loop is just a circular list of vertices. We can have faces with disconnect boundaries, like this one. And a fragment is just a list of connected faces identified by a unique fragment list. Then a region is composed by a list of fragment indices, and the model is stored and passed to the triangulator in the form of an XML file. We have here just a small piece of a typical file. We have the vertices here, the faces here, the list of fragments, and the list of regions. So this is how the model is input to our system. Well, once we have the model input, our algorithm works in 7 steps. First, we insert some auxiliary points to fill the empty space in order to have good-shaped tetrahedra. Then we perform a Delaunay triangulation of the convex hull. Then we have to recover the constrained edges that did not appear in the final triangulation because we are basically using a Delaunay engine. The same thing has to be done for the faces. Then we have to carve the final triangulation. We have to remove the tetrahedra inside the convex hull but outside the model. Then we have to classify each tetrahedron according to the region it belongs to. And finally, we have a phase of mesh improvement to try to improve the best as we can the produced mesh. The first step is just to insert a grid of points into the model. We can break either the edges, the faces, and the regions in order to have a triangulation looking like this. We have to fill the empty space. Typically, we would have something like this. We can see that the empty space has been filled by means of this grid, and we have, you know, kind of very well-shaped tetrahedron in these big empty spaces. We use an octree in order to avoid the insertion of a point very close to a face of the model, because this would generate a lot of bad-shaped tetrahedra, and basically our goal is to have a situation where there are at most 3 faces per cell. After doing that, each point is then tested against the face of the cells it interferes with before being added to the model. And we have a threshold used to find out the closest face to the given point. This is a model of the Venus, and just to show how the algorithm works, we have the restrictions, points, edges, and faces that must appear in the final triangulation. The triangulation of the convex hull can be seen here. Then we have a step to include the constrained edges that did not appear in the final triangulation. We can see those missing edges in blue here. In this case, are quite a few edges. The process that we use to force the inclusion of the constrained edges is just using a process called stitching, and we just insert a vertex in the middle of a missing edge. Since Delaunay triangulations have the nice property that the closest points are always connected by an edge, eventually this will recover all the missing edges. There are some convergence issues, but we can use protecting spheres in order to avoid a non-convergence process. The face recovery is similar. We can see here just 2 missing faces. And in this case, we have to intersect the missing faces against the tetrahedra it interferes with. And we perform a local retriangulation. In this case, we do not enforce the Delaunay criteria. From this point on, we do not have a Delaunay triangulation anymore, but this is not important here. The carving step is just a step to remove the tetrahedra inside the convex hull, but outside the model. And finally, we have a classification step where we need to classify each tetrahedron according to the region it belongs to. We just use a fluid field algorithm where we choose a point inside a seed tetrahedron, and using a pointing region testing, we can determine the region it belongs to. Then using adjacence information, we can propagate this information until we reach the boundary of the region. Well, when we have a mesh generated by this process, we have to improve the quality of the mesh. Since we used a Delaunay approach, we know that we can have some slivers which are bad-shaped tetrahedra. And slivers, in fact, they satisfy the Delaunay criterion, but they are mainly flat. They have 0 volume, and this may cause a lot of trouble in numerical simulations, and they have to be removed from the final triangulation. Basically, we have 2 main methods for mesh improvement. We have smoothing and topological transformations. Smoothing-based methods move some vertices to improve the shape of the incident tetrahedra. They do not change the mesh topology. There is the connectivity. Topological transformations, on the other hand, remove tetrahedra from the mesh and replace them by a new set of tetrahedron. In this case, the topology of the mesh can be changed. We have a picture here showing the Laplacian smooth, the most famous smoothing technique, where we move a vertex and all tetrahedra incidents to the vertex. And topological transformation generally are implemented using flips, 2 by 3 or 3 by 2. Well, smoothing methods belong to the numerical optimization domain, and topological transformations belong to the combinatorial optimization domain. In general, we apply both techniques together. And we also have implemented a hill climb method to optimize the quality of the mesh. In this case, we have to have a function to map each mesh onto a set of values which will describe the quality of the mesh. As we know, bad-shaped tetrahedra may ruin a numerical simulation, and slivers have to be removed, and it's not a simple task. Generally, we try to apply flips. That is, when it's possible, the simplest way to remove slivers. If the sliver appears on the boundary of the region, we can just use a peel-off. That is, just remove the tetrahedra because the volume is null. And we can also use smoothing to remove the tetrahedra. Hill climbing methods evaluate the application of a certain operation in a specific region of the triangulation. And if the quality of the modifier meshes is greater than the quality of the original mesh, then the operation is effectively performed. Otherwise, we do not apply the operation. Operations that do not improve the objective function are not applied to the mesh. And the hill climbing method ends when no operation is able to produce any further improvement. We have also implemented some scheduling algorithms to find out the order and number of operations to be executed by the hill climbing method. The scheduling also defines which set of tetrahedra the operations are going to be performed, and in general, it's performed in steps which apply a set of operations on all of the selected tetrahedra. Here we have some results we obtained using this methodology. We have the model of the elephant, the Buddha, and we have in the columns here the number of vertices, numbers of tetrahedra, number of bad elements before optimizing the mesh, number of bad elements after the mesh optimization, the time to generate the model, and the time to improve the model. In this case, we use just a quad-core computer with a frequency of 2.4 megahertz. And here, the same table. Here, the result using a geological model and a block used. This is fake, this is not a real model, but it would be a exploitation block. We have the type of grid we used to create the mesh, the number of points, number of tetrahedra, the time, and the quantity of memory used to produce the mesh. And here, sedimentary basin. We have two types of grids, number of points, tetrahedra, time, and memory consumption. Well, the main goal of this work was first obtain a robust implementation of a constrained mesh generator. And the main contribution of the paper was the creation of this scheme of breaking the model into fragments so we can put the polygonal surface directly into CEGAL. We also combined several scheduling mechanisms in order to produce a mesh in a reasonable time with a smaller number of bad elements. And we intend to proceed with this work, mainly looking for local and adaptive refining methods, faster scheduling algorithms, better sliver removal algorithms, try to use exact or inexact kernels in CEGAL, and we are willing to be able to process some huge meshes with hundreds of millions of tetrahedra. That's our next goal. Thank you.
there are any questions? Oh, I have a question. So is your experience that SIGAL is useful for industrial applications?
Yes, the main problem is the time to generate the mesh, especially if we use exact kernel. The time can, you know, be a little bit long. That's why we are trying to, you know, determine where we need to use the exact kernel and where we can use just the inexact kernel, because we can improve a lot the time to generate the final mesh here. But SIGAL is a nice piece of software.
So you recommend that for,
yes,
for mesh generation?
Yes.
Okay. Question?
And nice work. One of the, I have a question about the input data. One of the problems with geological data is that sometimes it may be very noisy, very a rough approximation of what stuff really is. So horizons may cross each other multiple times, create small pockets of false volumes, etc.
Yes, especially in basins, we have what we call pinch outs, very small angles. And that's why we do not want to round the boundary. We would like to have these small angles in the final triangulation so we can run the numerical simulation taking these into account.
Yeah, but what about two horizons, for instance, that they come together and they start to overlap each other, creating these
very small regions.
Small regions that actually shouldn't be there. Actually, one horizon should stop the other by erosion process or whatever.
These problems should have been filtered before input in the model.
Ah, okay.
We have another system that receives the polygonal surfaces, intersect them, and determine the regions. This is what we use to generate the XML file that will...
Okay. So, so you also have to handle, for instance, gaps in a pre-process.
Yes, but not here.
I see.
We have another system just to create the input for the triangulator.
Okay, thank you.
Any further questions? Well, if not, let's thank the speaker again.